Welcome to the Chapter 9 R Lab on support vector machines. We're going to start this lab by building a support vector classifier. Recall this is a classifier that uses soft margins and a linear separation hyperplane. So first thing we're going to do is set our seed. We're going to create some data. So X is going to be a matrix with a random normal variable with two columns. The number of data points is going to be 20 times 2, or the number of numbers it's going to put out. It's going to be 40 numbers, but because there's two columns, it'll actually make 20 observations with two feature variables each, one feature variable for each column. Then we're going to make Y, which is going to be our output variable, which will be this rep -1 10 times. It's going to repeat the number -1 10 times. And this will repeat the number 1 10 times, and then we're going to combine those or concatenate those with the C. And now we're going to take X wherever Y is equal to 1 and set that equal to itself plus 1. So this is going to take all the places where Y is equal to 1 and shift them to the right one. And then we're going to plot our data. And so this is plotting X, and then the color depends on the value of Y. And so we have our blue class, and then the places where Y was equal to 1 are shifted to the right by 1 unit, and that's why our red class is somewhat separated from the blue, even though they were generated by the same random normal variable. And you can see there's no linear separation between these two. So now we're going to create our data and put it in the form of a data frame with our X's and Y's, and we're going to load a library we need. There's a good chance you will have, the first time you run this, a yellow bar across the top that allows you to install the E1071 library. And so you install it from there. Then we are going to submit, so we're going to fit our support vector machine, but we're going to do the kernel equals linear, which makes this the support vector classifier. And the parameter that the SVM in the E1071 library takes in is called the cost. So this is not the C value that we looked at in the Isler textbook. This is a cost that tells you the cost of observations violating the margins. So a higher cost means fewer observations will violate the margins. So let's fit the data, and now we're going to plot the fit. And this plot doesn't tell us what's classified correctly or not. What it's showing us is the classification regions, the linear separation, and then the observations that are the support vectors are shown in its X's. And this command here, svm fit $index, that will tell us the indices for the support vectors. So we can see that there's 7 of those. And then we can get a summary of the support vector classifier that we just created, the function call, the parameters. It tells us there were 7 support vectors. We didn't tell it to use 7, we told it the cost, and that cost resulted in 7 support vectors, 2 classifiers, and the levels are -1, -2. Let's run this again, but the cost will be 0.1 instead of 10, so it's lower cost. With lower cost, we see more support vectors. You'll notice in the plot that's shown, there are a greater number of X's. We list them, we see the indices, and we see there are more support vectors. This library has the ability to tune using cross-validation, so we're going to tune the support vector machine with our kernel linear, so it's a support vector classifier, and the ranges that we're going to tune by are going to allow the cost to run over this set of values. And then we're going to get a summary of those tuning, and this shows us the cost for the different cost values that we looked at, and then the error for those different costs. And we see the lowest error occurred when the cost was 0.01. And so we can pull out the best model from that tuning. And so this is a process of parameter tuning, testing a number of different parameters. Sometimes we do it manually. This is very nice that this library comes with a way to do it automated and pick the best model. Then we get the summary of the best model, and has 16 support vectors. And scroll down so we can see. Now we're going to build some new data. And we're building this to make a test data set. And then we apply our best model using this prediction to this test data set. And then we can get a table that tells us how well we did. And we look along the axis. These are the observations that were correctly predicted. So these were 9 were negative ones predicted as negative 1, 8 ones predicted as ones, and there were 3 errors. So that's 17 correct and 3 wrong. Let's use a different value for cost. So we're going to use this line and predict with this. And we see with this cost value of 0.01, remember the best model was 0.1. With this cost, we have 14 correct and 6 wrong. So we're getting results that are not as good as we expected. The tuned model using cross-validation gave better results. Now we're going to generate some new data, put this new data into a data frame, and look at some different results using different costs. So in this example, what we see is perfect separation. There are no errors in this prediction. But when we look at this separation with this line, it has 3 support vectors, and the margin is very small. And if we look at these two classes, this might not be the best line. So we're going to raise the cost to 1, which will allow a greater number of support vectors, or effectively a larger margin. And let's see how that gives us. If you look at those two classes in this plot, you might imagine a better separation between these two classes might go through where I'm drawing with the arrow here, as opposed to the line that's drawn here. Even though this gives perfect results, there's a number of observations that are right on that boundary, and we might get something robust with a different boundary. So here we're going to redo our support vector classifier with a higher cost that uses more support vectors, and we get a result that's probably going to be more robust. So that concludes our work with the support vector classifier. Let's look at some support vector machines. So this allows us to use different kernels other than the linear kernel. So we set our seed, we make a matrix of 200 observations. Here we're going to build our data. Similarly, we have some normal distributions, and we've shifted some of them. We've put them in a data frame, and now we're going to plot them. And see, we have the red data points in the middle, and then the black on either side. So there's no separation no linear separation that's going to separate these. When we look at where this data came from, we made 2-dimensional random normal variables. And we made 200 of them, and then we shifted some to the left and we shifted some to the right. So there's not any nuanced structure separating these. So the separation between these should be a linear on either side of the red, and everything in the middle should be red, and the things on the outside should be black, just knowing where this data came from. Okay, so we're going to create a training set from this, and we're going to fit our support vector machine using a radial basis function as a kernel, and gamma equals 1. That tells us how far out, how quickly that radial basis function drops off, and then the cost equals 1. And so let's plot the results from that. And so that cost equals 1 resulted in, let's see how many support vectors we have. We have 31 support vectors, which gives us more robust estimation of the decision boundaries between our classes, and we knew this should be something linear, and these boundaries on either side look pretty reasonable, separating between our classes. Let's reduce the cost. This is going to use fewer support vectors, and let's look at the results. And using those fewer support vectors, we have in this plot what appears to be a less robust separation between the classes. Knowing where this data comes from, these are not the curves that would be ideal to separate these classes. This is overtraining because we chose a cost function that was too small. And I'm going to jump up and let's get the summary and see how many. So there were 16 support vectors here. Remember before, what do we have? Our support vector machine that looked good had 31 support vectors, which gave us more robust results. Here we only have 16, and so that doesn't work as well. Okay, now let's reset our seed. Now we're going to use this tune in the library that's going to tune our support vector machine using a radial basis kernel, and it's going to run our parameters over this list, where the cost is going to run over these values and gamma is going to run over these values, and let's see what the best classifier we get is. So here's the summary of our tuning running over the different cost and gamma values, and the error is in that column. So what do we have? A 0.07, 0.07. So we seem to have a couple of parameter settings that give us 0.07 as our error, and we can look at the table of our training and test data, and we see 67 plus 21 correct and 12 incorrect. So we're about 88% correct on our test data, right? So this is taking that value that those values for the cost and gamma that we found using the tuning, using cross-validation, and applying them from where they were tuned on the training data and applying them to the test data, and we're getting good results. And now we're going to generate some Roc curves. So to generate Roc curves, we're going to use this library ROCR. Like many things in R, there's multiple ways to generate Roc curves. We're going to use this particular library. And so we need to read in the library. We're going to create this ROC plot function. You input your predicted values and the truth values, and it's going to create a Roc curve. There's something that's winding up with the axes. It's wrong in this plot. So we're going to execute this and follow this through according to the textbook, and then we'll take a look at what we could do to correct what's not being plotted right. So the first thing we do is we fit our support vector machine with a radial basis kernel, gamma equals 2 and cost equals 1. And so we're using our previous generated data. This par command creates 1 row, 2 columns of figures to plot. And so here's our Roc curve plot. And so something's not correct in this plot. The curve is going to the right and then up. So a Roc curve should go up and then over. And what this curve is suggesting is as you increase your threshold, your false positive rate goes up a lot without increasing your truth positive, and then your truth positive rate goes up at the end. So it seems these axes are switched. What you should have is your true positive rate going up, and then your false positive rate going up once your whatever variable you're thresholding on gets high enough to start pulling in false alarms. So we can get this to look a little better by switching these. It's not going to fix things because on the standard Roc curve you have true positive rate here and false positive rate here. Switching these two in the Roc plot command switches the variables, but it also switches the axes name. So we're going to keep plotting like this, but you have to ignore the axes label. This is true positive rate here and false positive rate. We're thresholding on the distance to the margin, and as you increase that distance, you increase your true positives. And once that distance gets far enough, then you start pulling in some false alarms as you go across here. And so in general for Roc curves, up and to the left is always better. So now we're going to train on a support vector machine. Now we've set gamma equal to 50. And this is still on our training data. And so plot our results. When gamma is 50, we get perfect results. Now we're going to pull in, before we were using our training data, right, train right there. Now we're going to use the test data, which we input by doing negative train. That means not the training data in R. And so there's the plot on our test data using gamma equal to 2, and then on our plus test data, there's the result with gamma equal to 50. So what we see is on our training data, gamma equal to 50 looked better, but on our test data, gamma equal to 50 looked slightly worse. So maybe this gamma equals 2 is better, and it'll give us better generalization. It's going to generalize better. And those are how we generate some Roc curves using R. Thank you for watching.